Hi everybody, so in this video I want to discuss how we can take what we've learned about solving second order linear differential equations that are homogeneous, so we've got zero with constant coefficients. Let's review that to see how we can extend this and apply this to higher order differential equations that have the same form. So just to recall, when we were solving differential equations, such as this one, step one was to set up the characteristic equation by bringing the coefficients, the constants from the differential equation, into their appropriate slot in the characteristic equation. And then we find solutions to that quadratic equation. And for quadratic equations, we're either going to have two distinct real roots, one repeated real root, or two complex conjugate roots. And so depending on what situation you're in, then you would take the solutions to that characteristic equation and substitute them into the correct form of the general solution. So for two distinct real roots, we had a form that looked like a sum of two exponentials where the powers came from each of those roots. If we had one repeated real root, then for the second term, we multiplied by this term t. And when we had complex roots, then the real part we plug in for alpha, and the complex imaginary coefficient we plug in for beta. Now what I want to investigate for the rest of this video is how can we build off of this technique to solve higher order differential equations, such as third order differential equations like this. And so what I mean by similar, we have constant coefficients and this is homogeneous. So let's now investigate how we can apply similar techniques to solve this differential equation. And so what I mean by use the same process. So if we have a third order differential equation, first we're going to set up the characteristic equation, and now it's going to be a cubic polynomial. So the highest power, we have a degree 3 term corresponding to the third derivative in our differential equation. Then we find solutions to this characteristic equation. For quadratics, we have a nice tool like the quadratic formula. Most people are not familiar with the cubic formula. There is one, but typically we would use technology. So you're welcome to use a graphing calculator or Python if you want to program this, or GeoGebra to plot the polynomial and then look for the zeros of the polynomial on the graph. So I'll solve this one algebraically just to see what it would look like. So the characteristic equation here would be r cubed. So we have a 1 over here. We have a minus 5. We have a minus 4 and a 20. And what we want to solve is for what values of r is this equal to 0. And again, we could feel free to use technology to solve this, but we can try and factor this in a nice slick way. So for example, I can break up these four terms into r cubed minus 4r and then the minus 5r squared and the 20. And now I can pull out a common factor in each of those terms. So I can pull an r out from the first one and a minus 5 out from the second one. And now we can see that they share a common factor in each of these terms. So then we can pull out the r squared minus 4, and then what's left is r minus 5. And now, finally, we can factor that quadratic one step further, and now we've factored this cubic polynomial into 3 linear factors. And so for each of these factors, we get a different root. And so in this example, the 3 roots we have, from this one we have 5, from this one we have 2, and from this factor we get a root of minus 2. And then we plug these roots into the correct form for the general solution. And so what I mean by that is when we have 3 distinct real roots, then we're going to use a similar form for the solution, which is the sum of 3 exponentials with the powers coming from each of those roots. If you get a repeated root, then you would use the same trick with multiplying by t. And if you have a complex root, then you would get the Euler's formula would come into play, and you get the e to the alpha t times cosine beta t times sine of beta t. So let's take a look at one more example on the next slide if you want some more practice. So for this example, we're going to take a look at a fourth order differential equation. So this notation here means fourth derivative of x minus 5 times the second derivative of x minus 36x is equal to 0. So we have constant coefficients and it's homogeneous. So we're going to apply the same technique, which is first we take the characteristic equation for a fourth degree. For a fourth order differential equation, we get a fourth degree polynomial. Then we would factor this or solve the equation. Probably you would graph this and look for the zeros, or you can try and factor it. And so in this one, just to quickly show the algebra, we could factor this into two quadratic factors, and one of the quadratic factors can further be factored into two linear factors. So this fourth degree polynomial factors into r minus 3, r plus 3, r squared plus 4. So from this linear factor, we get a root of 3. From this one, we get a root of minus 3. And from this one, we get complex conjugate roots of 2i and minus 2i. And now that we've got the four roots, we substitute them in to the appropriate form for the general solution. And so for the real roots, we take the 3, and that goes right here. We take the root that was minus 3, that goes over here. And for the complex roots, we have e. In this case, our alpha is 0. So I'll just put this in as a placeholder for now. So we would have e to the alpha t cosine 2t, where this comes from the 2 over here, plus c4 e to the alpha t sine beta t. And yes, we would want to take those e to the 0 t's and just simplify them to 1. And so here we have our general solution, which, as you might note, has 4 arbitrary constants in the general solution. And that's because we have a fourth order differential equation. So if you wanted to solve for all of these coefficients, we would need to be given 4 initial conditions in order to solve for these 4 unknowns. Okay, see everybody in class.